as you might have noticed, I'm an AI-generated avatar. Today, I'll present you this edition of the festival. Over the next 3 days, we will explore the horizons of intelligence. This is the theme of the 13th edition of the Scientific Research Festival. At Trieste Next, we will discuss both human and artificial intelligence, ethical boundaries, and the new frontiers science is facing. Where will artificial intelligence take us? What impact will it have on research? Medicine, robotics, astrophysics, food and nutrition, and the environment are just a few of the scientific fields we will delve into at Trieste Next. This is the central theme of Trieste Next, featuring over 100 events in English and Italian, the Literary Award for the Scientific Book of the Year, and 70 activities for schools. More than 300 internationally renowned speakers will be in Trieste. And don't forget to visit the 40 exhibition spaces and open labs in Piazza Unita. Before we welcome the guests of the next event, on behalf of the organizers and co-organizers, I would like to thank all the scientific institutions of Trieste, City of Knowledge, as well as the institutions that collaborated with us. A special thanks goes to the festival's main partner, the partners and content partners for their crucial contributions. Thanks also to the media and technical partners. Lastly, a heartfelt thanks to the 200 volunteers who made this edition possible. One final note. I'd like to remind you that the next session will last 75 minutes, with the final 15 minutes dedicated to your questions. Please also remember to check the updated event schedule on www.triestenext.t, which you can access via the QR code. Enjoy the event and have a great festival.
Hello guys, good morning to everyone. Thank you for being here. This is the panel of the poster presentation dedicated to international students for the Academy project. I'm Michelangelo and good morning again. Here we have some of your colleagues, PhD students who were selected for presenting their research here in Trieste. I would like to spend some words about this event since 2022, when we realized that many of students selected for the International Academy were promising researchers. We decided to give the opportunity to you to present the research among peers, all of you guys. So that's the aims also of Trieste Next, a festival who tries to give the opportunity, chances to meet researchers, journalists, many people from all over the world, in order to give you the opportunity to understand your fields better and better and better. So now we are with Sara Battiston, with Estela Español, then Gilberto Goracci and Luigi Piero Di Bonito, 4 students, PhD students. And we would like to start with Sara Battiston for her presentation. We have 60 minutes and the last 15 minutes are for you guys, for your questions. So please, let's create a good conversation about what you are hearing from this panel. So Sara, you are a PhD student of Statale, Milano University, in development of generative models for creating synthetic ECG data. Yes. For in medicine fields, right?
Yes, exactly.
Would you like to explain us your research and hear your PowerPoint? So let's do it.
Okay, so thank you. As he say, I'm Sara. Hi everyone. And here today I'm trying to explain what I did this first year of my PhD in my laboratory, which is BISPAB at the University of Milan. And we were trying to answer this question. So, can generative AI improve the trustability of deep learning models? And we provided a use case, a proof of concept if you want. So let's start. What's generative AI? Wikipedia says that it's an artificial intelligence capable of generating text, images, video, through means in response to prompts. What is important is that they learn patterns and structure of the input training data, and they generate new data through these. So you know the example ChatGPT, stable diffusion, you know the filter that makes you old, that's called style transfer. And the idea is to apply this generative AI to physiological signals, which is a set of all of those biological processes in the human being that can be measured. So for instance, brain MRI or ECG, blood drawings, or whichever the hospital gives you whenever you pay your bills. More in general, artificial intelligence in healthcare is a very promising sector. It is used in telemedicine and remote monitoring. It's used in drug discovery and development. For instance, think about AlphaFold. It's used in precision medicine, so personalized and customized treatment for each patient. Virtual health assistance, you know, chatbot helps in psychology. Public health predictive analysis, COVID outbreaks, for instance. And lastly, to support clinical decision. This is the case for every classifier exploiting medical data. All of this is promising, but we have to remember that AI mistakes can actually harm patients. And they have to comply to GDPR regulations, which is rather strict. And most of all, deep learning algorithms are often hard to trust. But why is it so? Well, whenever we as a scientist train a deep learning model, we take whichever data we have, which might be signals, images, structured data, we organize them in a data set, we think about the model, we train them, we validate them, and we have all of our nice metrics. And then when we give it to the doctor, he puts inside the data he has, he sees this black box with an AI patch on it, and he receives just a number and a diagnosis. So the doctor is like, how is this machine making the decisions? Can I trust it? A big problem with this kind of black box models is that bias can be hidden within the model. What does it mean? It means that the model makes a decision, but maybe it's making a decision not based on the feature we would have chosen to make such decision. Famous example is it was trained this classifier to distinguish huskies from wolves. And they found out that the wolf classification was based not on the face of the wolf, but on the snowy background. So this is the type of bias that we'd like not to have in our models, because we'd like for patients to be correctly identified in their disease. What if we could exploit generative AI to improve the trustability in this sense? The data we use in our project are electrocardiograms, so they're fast, cheap exams. They need an expert to be read, and AI can help in the sense that we have deep learning classifiers for that. And we consider myocardial infarction classifier versus healthy subject or norm. How can this generative AI help? Well, we saw the example of generative AI getting you older, or in this case, transforming horses into zebra. And we applied it to transform real myocardial infarction signal into a normal synthetic signal. The advantage is that we do not need any specific domain knowledge, because the network is good at interpreting the ECG and choosing the feature and modifying exactly the feature we want to transform a myocardial infarction into a normal one automatically. And it also keeps the characteristic of the specific individual. So the idea to identify if a model is biased is that we have a real myocardial infarction ECG, and then we apply to it style transfer and make it healthy. So this healthy ECG has exactly the modification occurring in the features we'd like the model to identify. And with both this ECG, we classify both of them, and we compare outputs. If the outputs then are different, then I can trust this classifier, because upon modification, it changes its mind about prediction. But if the output probabilities are the same, then the classifier didn't identify the ECG based on the feature we would like. But here, we're making a very interesting claim. So this style transfer function creates ECG that are plausible, so real, and that they morph the characteristics that we want. The advantages of this method is that each hospital can test it with their own data set, and it helps to prevent data shift, which is an occurring problem when testing with different populations. It does not depend on the classifier, so that they can test it with whichever classifier they were given, and we can reuse this model in different contexts. For instance, a person is arriving to the ER with chest pain. He gets done an ECG by the doctor, and the doctor is not sure whether this ECG is a myocardial infarction. So he throws it to the generative network, and he looks at the normal one, and he compares them, and then now he's sure that's a myocardial infarction because his normal ECG would be very different. The disadvantages, though, is that the training requires very large amount of annotated and high-quality data, and this is expensive. And the network design is not trivial. It requires quite a lot of effort. These are some of the results. I'm not going into detail, but the idea is that if the output probability are all around 1, then we have a trustable classifier, while if the output probabilities are all around 0s, then the classifier is not trustable. So we made a claim. This claim involves data validation. We have to validate the synthetic data we generated then. What ones usually do is ask doctors, but this method is expensive because you have to pay them most of the times, and it's slow because they're very busy. You can use AI-specific explainability methods, but they're not easy to customize to your own generative network, and often it's not clear what explanation means in AI in general. Or you can check literature, but there's no general consensus, and they're not model agnostic. They're specific to whatever the author is doing. So we, like many others, we define some methods ourselves. The idea is that we are using 2 visually inspected methods in order to check whether the distribution of the real and synthetic data are somewhat comparable. Then we evaluate one of the specific features that we wanted to be modified and also check if that is plausible enough. And then we have a metric tied to the specific model of generative network we're using. The advantages is that 3 out of 4 of these methods are model agnostic, so they don't depend on the generative network use. They're quick to implement, and they yield very fast results, thing that explainable AI not always so much, and they do not require a doctor to validate them. Although if you have one, exploit it. These are some of the results, just to show. Again, I'm not going into any details about it, but the first 2 plots are about the visualization. And here we can see that the synthetic data, which are the red bands and the red dots, are kind of respecting the distribution of the real data, which are the blue band and the heat map in the background. They are similar enough, so we're fine with this data. And the plot on the right, the radar plot, is the evaluation of the feature we wanted to obtain. And this also tells me that the feature has been generated good enough. So the data that we generated are fair enough. Not the best, but fair enough. So the conclusions we reached so far is that generative AI can actually be exploited to clarify the decision-making and to spot biased models, and that the customization of a neural network, of the generative network, can help generate implausible signals. But we need very large and nice data set. And whenever we are generating data and using it in a medical field, it is fundamental that you assess the quality of the synthetic data you have generated, because lives are at stake. For the future work, we will extend this paradigm for ECG with several different abnormalities. We plan on improving the cycle gun and generated better signals that can be better. And we will investigate new methods to assess data quality. And the idea is then to try different type of generative network. So thank you very much. If you're interested, This is the QR code for my lab. So if you're interested in the topics and would like to know more, please contact us. Thank you.
Thank you so much, Sara. So interesting. So guys, if you have questions, just keep it, and then at the end of the other presentation, you can do it. Let's move on Estela, Español from Spain, Università de Valencia. She's a PhD student again, and she's studying the application of AI for biomedical solutions, right? So again, in these fields, would you tell something about your research, about this microscope that you built on?
Thank you. Good morning. I'm going to stand up. So first of all, let's imagine with me that you have a thick 3D sample and you want to image it. But then you are seeing it and you want to see the details in the sample, but are below the optical resolution limit of your eye. So therefore, you need to use a subjective optical instrument, which in this case, it's going to be a microscope. So once you have your sample, which can be a biological sample or a sensor or whatever you want to see, you put it under the microscope, and to focus each plane of your sample, you need to move either the sample or the microscope objective or the stage to get an image, a clear image of each split. What happens? That if I have my sample in a liquid medium, the sample moves around when I'm mechanically moving it around. And this causes some vibrations, and it's time-consuming until we wait that the sample is still to capture all the images. For that, we propose a system which is based on an electrotunable lens, which is basically a lens that throughout a voltage, we can move its shape and focus different planes. This avoids these vibrations, and it's faster, and it's not time-consuming, therefore. So how do we place this lens in the exact plane? We need to place it strategically to get to our image. Oops, is it pointing? No? Okay, no?
I think that the light will,
yeah.
It's not so hard for the...
So you're going to have to follow me. So first of all, what we did is to build a microscope. A microscope, it's nothing else than just a microscope objective and a tube lens. Because when light coming from a source, it goes through the infinite, and therefore we need a lens to focus it on a plane. In this case, our sensor. Once we have built our microscope, we just keep on adding lenses to make it bigger, to get the image just focused on the distance that we need up to our sensor. So in the image below, down here, the second one, you can see how we are moving the tube lens closer to the microscope objective, because in a real microscope, a commercial one, you don't have like such a big structure, so we need to be short and small. Then we add two equal lenses, which are called in the diagram as L1, as L2. And then in the middle, we place strategically our ETL. Therefore, the image is going to be projected into the sensor, and we are going to be able to capture it computationally. So that's the design. That's our idea. So what do we do next? We do a proof of concept. With that, we used an USAF test, which is nothing else than a resolution test, which allows us to know how good our system is resolution-wise. So first of all, we did this imaging without the ETL, and we can see the image beneath, which is quite far, right? If we have something small, that's not going to be good enough to see all the details of our sample. But then we placed the ETL in the system, and we put voltage, a singular voltage, which indicates that in our sample, it's going to be 2D. So we are not even going into the 3D system yet. And we can clearly see that the resolution test, it's getting into its lowest point. I mean, it's not super clear in this picture, but you're gonna have to trust me. And then we used a spatial frequency response test, which is the slant edge test. It's nothing else than comparing, how to say it, like black and white kind of imaging. And we can clearly see in this comparison as well that our system gets a smoother frequency response towards the details. So for the proof of value, what we did is to take some samples. We took stained samples, not biologically, but just like some raw material, and we observed it underneath the microscope. And then to get into the more biological, we got some mice brain slices, which were given from another laboratory. And we could clearly see that indeed we were able to acquire a set of 62 images of this brain, which is down there, which I don't think you can really see it either. But we took the whole stack of pictures, which again, it's 62 pictures, just changing the voltage of the ETL. So how amazing is that, that just like moving 0.5 voltage, we can get a reconstruction of the image. But again, it requires a computer vision tool. And we are now at this point. So we did the registering, which is just to put all the images together and align them. And we got a depth from focus, which just means that we get in each plane the focused section of the image. And we were able to obtain the resulting reconstruction. So why it's interesting to use AI models in these kind of systems? Just because you don't need to be using your time to get all these images refocused or to being able to acquire the desired image. But since we are talking about images, and of course we need to go to a black and white, which again it's just zeros and ones to say like that, and we need to pay attention to the pixels and everything, we need to adapt the current models that are available to get the desired resolution of our image. So at this moment, we are just working with other biological labs to get more samples and to be able to establish a model that is really useful for a several set of samples. Thank you.
Thank you so much, Estela. Here we have Gilberto, Goracci. Everyone here, each of them use the AI to to implement their studies. So this is quite interesting, just because we can understand how AI is in our life, in our studies, in our work, in our job, in our field. So let's just an advice. If you don't focus on it, I think you may start studying for your job and for your ordinary life, just because it is something really, really useful for all of you. And also for Gilberto Goracci and Ivan Agostinelli, the research is from both of you. So Gilberto, PhD student from University of Rome, right? You're about to finish it, the PhD program, and here we're not talking about medical sciences or biomedical fields, but space, right? So let's start. Thank you, Gilberto.
Okay. Thank you. I'm Gilberto. As Michelangelo said, I'm a third year PhD student from the School of Aerospace Engineering in Rome. And today I will talk about how we apply AI to space science. If you think about space, you probably think about a big empty space. But this is actually not true anymore, because the space is full of things that you don't want. For example, satellites that are not in function anymore, or space debris. All those kind of objects actually need to be categorized, recognized, and identified to prevent, for example, collisions. You don't want your satellite to be hit by a piece of painting, for example, which in space can cause a lot of damage. So there is this field called orbit determination that studies how we can track the space debris when we see them in space and try to reconstruct their trajectory in order to avoid or establish the probability of the collision. So in the initial determination problem, we have limited observation available to characterize the motion of an RSO. RSO is the resident space object, and to give a preliminary state of the target. So there is this problem that is called very short arc or too short arc problem, in which you have very short amounts of measurements available to reconstruct the orbit of this object. Think about, you see a little tiny dot in space, you look at it for 20 seconds, and you must be able to reconstruct its trajectory, so where it will be in 1 month, 2 months, and so on. So it's a very challenging task. Here we can just skip this slide, it's just a bit of mathematics. So to resolve the too short arc problem for orbit determination, we consider the Earth as an ideal sphere. We know that it's not like this, but for this approximation is correct. And we ignore the rotation of the Earth. So we have just a simple Keplerian gravitational motion. So it's very simple to model. And here, just a little bit of more mathematics. We need to estimate this quantity that's called the range, this indicated by the rho letter. That is basically the distance between the observer in space, so your camera fundamentally, and the target. And this is very challenging because, as I was said before, your available measurements are very, very limited. So this is why we developed the YODA algorithm, the initial orbit determination with artificial intelligence algorithm, that must do this orbit determination. So how does this algorithm work? We have a meta-heuristic module first, which is based on the artificial bee colony algorithm, that is a kind of genetic evolutionary algorithm, which is used to retrieve a first orbit estimate of the object. This orbit is not the best, often is very not accurate, okay? So it needs to be refined. In order to do that, we use the physics-informed module, which is based on a physics-informed extreme learning machine. We'll talk later about physics-informed neural networks, which are a very promising framework for AI. This module is used to improve this estimate given by the meta-heuristic module, and it actually, we found out it's very, very accurate. And then we have an outliers removal module. We will talk about it later. So, how does the meta-heuristic algorithm work? We have a population that is randomly generated. Look at the image, every point, every dot in that plane is an orbit, okay? Each middle of the population is a solution of our problem. And we generate it not totally randomly, but for example, in a kind of admissible region. For example, you don't want to generate an orbit that is inside of the Earth, because that makes no sense. So we can use a loss function, evaluate it for each individual to know how much this individual is actually a good candidate to be the right solution. The most promising individuals are then used in the next iteration to refine the solution. So how you can see here, the generated populations actually converge near the true value of our solution. The artificial bee colony algorithm is a kind of optimization algorithm which tries to mimic the behavior of foraging bees. We have 4 components in this model. The first one is the food sources, which are basically the solutions of our problem. And they produce nectar proportionally to the fit of the solution. So the right food the right food source, for example, will have a very good amount of nectar. The employed bees, they search for new food sources with more nectar than the previous one. The onlooker bees select the food location which have a greater chance of having high nectar. So it's like providing extra exploration around the most promising sources. And then we have the scout bees. They just go around randomly and try to find new food sources. Then let's move on to the machine learning part, to the extreme learning machine, which is basically a learning algorithm for neural networks with a single hidden layer. Neural networks are generally very complicated because the final output is some kind of linear, non-linear combination of the previous layers. So they are very difficult to understand. Sometimes when you're working with a neural network, the output doesn't make sense. Then you change a hyperparameter and then you find a better solution and you don't actually know why. In the single layer neural networks, this problem is a little bit it's a little bit smaller because you have just one layer and you have more control of the analytical side of what you are doing. So what we need to know from this slide is basically the output of our network is a matrix H times a matrix of the weights that we call beta. And there is all a theory behind this extreme learning machine that allows us to find the optimal weights for our network, which are given through the pseudo-inverse H of this pseudo-inverse matrix of the H. In physics-informed frameworks, we actually embed the physics of the model inside the loss function of the neural network, and this is what makes them very powerful. Generally, your loss function, all neural network approaches and deep learning in general tries to minimize a loss function, okay? And this minimization basically compares the true solution, the target solution, with the predicted value given by the neural network. But that makes them sometimes very hard to understand because you're just comparing output. There is no intermediate process. In physics-informed neural networks, actually, you can put physics equations inside your loss function. So the solution that you find actually comprehends the physics of your problem. So if your solution, in this case, the orbit, doesn't make any physical sense, so for example, you have an orbit that goes inside the Earth, the training is penalized. This is why these frameworks are very suitable for this kind of problems. So this is the meta-heuristic module more in details. We used as optimization variables the ranges that I talked about before. So we generate a set of random ranges. We use this loss function here to see how much they are good, actually. And then we keep the best ones, and we generate the population again in order to find the first orbit estimate. Then we use this meta-heuristic estimate, RTMH, in the upper left side, to initialize the physics-informed extreme learning machine. In this way, we have a loss function here that is actually a composition of two terms. We have a loss that is relative to the dynamics, so the Keplerian motion of the satellite, and then measurement loss, which is given by the difference between the line of sight that we measure and the line of sight that we predict. The line of sight are basically the direction between the observer and the target, so the direction you are looking at. So in this way, we can find an orbit estimate, and then there is this alpha algorithm, which is an adaptive loss function algorithm that is basically just a way to adapt the training of the neural network to take into account more factors and make it more robust and trustable. This process is repeated for a fixed amount of times because for each object that we analyze, we want more than one estimate, okay? So to add statistic and to add robustness to the random parameter initialization of the frameworks. So this is the PM scheme, but it's way too complicated. We don't need all these formulas. And here we have an outliers removal module because some of the solution we find may not be correct. For example, the physics-informed extreme learning machine may not converge. So it just gives a solution that makes no sense. And we want to remove that. We use the loss function values to filter out the solution that we think they are not correct. And we try also to find some metrics, for example, the mean values of the solution, the standard deviation of the solution, and all this stuff that can be useful somehow. So we tested this algorithm on a Monte Carlo simulation. We generated 1,800 orbits. So this is a very nice image, I think, for a subsample of 500 generated orbits with random observers and target. And we consider a variable length of the observation that goes from 20 to 60 seconds. And we evaluate this algorithm on the percentage of success, so the error on the final target estimate is lower than a certain threshold, and the mean root sum square error across the observation arc. So here you can see the comparison between the Yoda full algorithm against only the meteoristic module. As you can see, the meteoristic module is almost always not sufficiently accurate, and this percentage tremendously goes up when we apply the physics-informed extreme learning machine. So here we consider a case, a correct case, if the error on the final target state is lower than 1 kilometer on the position and 1 meter per second on the velocity. So as you can see here in this slide, we have some other results in terms of mean position error. So we take all the arc, all the measurement, we evaluate the error at each point of the arc, and we do the average of these values. As you can see from the histogram on the left side, the majority of the errors of the Yoda algorithm are focused between 0 and 0.2 kilometers, that's 200 meters. If you consider the geometry of the problem, you are looking at targets that are very far from you, like they can be also 3,000 kilometers far from you. And having error lower than the kilometer is actually a very good estimation. So maybe the results can change if I consider different length of the observation, for example, 20 seconds or 30 or 40 and so on. Thankfully, this is not the case. So as you can see, the percentage of success of the algorithm doesn't actually depend on the length of the observation. And this also shows robustness and effectiveness against all these parameters. Finally, here we did a grid search of the performance of the algorithm for different thresholds on the final target state. For example, the lower right panel corresponds to a very small threshold on the velocity and the position. So you can see that if you consider, for example, 0.001 kilometers, that's 1 meter of precision, the algorithms are not capable of reaching that level, which is absolutely normal. The box highlighted in white is the considered thresholds for the results that you saw previously. So you can see that even if we enforce the thresholds a little bit, so we want more precise result, for example, 1 meter per second and 10 meters of precision, we still have 89% of probability to retrieve the correct orbit, which is a very satisfactory result for us. So here you can see a visual representation. In the light blue, you have the observer target, so that is where your camera is, the orbit of your camera. The red one is the orbit derived with the meteoristic module, and the true orbit is in green, which is actually superimposed to the blue orbit, which is the Yoda estimate. So visually, you can clearly see that the orbit is retrieved perfectly. I mean, from this distance, perfectly. So to conclude, we developed this Yoda algorithm to do initial orbit determination to solve the two short arc problem. This algorithm is a combination of meteoristic and physics-informed framework to retrieve a very precise orbit estimate. And we tested it on a very big amount of cases, from 20 to 60 seconds. And 1,794 out of 1,800 times, the algorithm retrieves the correct orbit with an error that is pretty satisfactory to us. Future developments will include the implementation of further submodules to have an autonomous evaluation of your algorithm, because right now the algorithm just gives you a result. So this is the error, this is the position. But it doesn't give you like a probability of this. So the algorithm says that the position is here, but it doesn't give you like with this probability, with this error, and that's something that you would like to have, for example, when you validate a model, when you validate an algorithm for real life and real applications. So also we would like to test this algorithm actual real data. There are several catalogs of satellites with their position in time, so you can use the data and test the algorithm on real data actually. So thank you for your attention.
Thank you so much, Gilberto was taking notes, by the way. Really, really interesting. Also, thank you, Ivan. And the last one is Piero Di Bonito from University of Campania, Università della Campania, a PhD student who is finishing also. And again, AI applied in another field. So Piero, would you like to introduce your work?
Morning. My name is Piero Di Bonito. As Michelangelo said, I'm finishing my PhD program at the University of Campania Luigi Vanvitelli, and just to be clear, I'm not a data engineer, an artificial intelligence engineer, I'm a chemical engineer. So today I'm going to talk about application of explainable artificial intelligence in chemical engineering. Why? But before to talk about explainable artificial intelligence, go back and why artificial intelligence-based methods. If we search on Scopus the keywords machine learning, deep learning, artificial intelligence, we can see that in the last year the total amount of paper is increased related to scientific publication. As we can see here, is increased up to the 5,500%, and we can attribute this kind of growth to the release of maybe today, the most used Python machine learning library, scikit-learn. This release has been done in the 2007. Another key event is the release of the Explainable Artificial Intelligence program by the DRPA. We are talking about something which is born before our AI Act, okay? So what is Explainable Artificial Intelligence program? XAI is a set of processes and methods that allow human users to comprehend and trust the results and output created by machine learning algorithms. XAI is crucial for an organization in building trust and confidence when putting AI models into the production. So we are going to talk about the introduction of artificial intelligence in industries. So we can distinguish artificial intelligence before XAI, after XAI. Before XAI, where the outcomes were not explainable, after XAI, where the outcomes of AI algorithms are explainable. We can build trustability, we can build explainability into way, using intrinsic explainable model, such as linear regression, logistic regression, decision trees, or using an explanation interface post-hoc. Also the methods that Gilberto showed before about physics-informed neural network, we are talking about intrinsic explainable model. Now, the application is to build an innovative approach into design of chemical plants. What I'm going to show you now is the conventional design pathway, starting from the behavior of complex mixture, analytical methods for the design of chemical plants, and the direct experience from previous design. All these things together can go through a preliminary project, a prototype, a lot of experimental tests to have the scale up of the plants from lab scale to an industrial scale, and at the end, the industrial plant project. Our approach wants to use XAI methods, also using lab data and industrial data from soft sensor, because a lot of companies, they have a lot of data for the operating condition of their plants, and in this way make an innovative design pathway. Our case study. Our case study is a case study based on the environmental sustainability, because we are talking about the shipping companies. So maybe, as you know, the ship can emit a lot of pollutants inside the flue gases, okay, such as SOx, CO2, particulate matter, and NOx. A lot of them, in particular SOx and particulate matter, we can enumerate these effects to the type of EV fuels which the ship burns, okay? But starting from the 2023, the IMO, the International Maritime Organization, make new regulation about the sulfur contents of the heavy fuel in order to avoid the emissions. So starting from a 3.5% of sulfur content, we need to go to 0.5%. So how to comply? Maritime companies have two choices to respect requirement. Both are driven by huge investment. Why? Because you need to use or LSFO, so low sulfur fuel oil, 0.5% in terms of sulfur of content, so very expensive, or use the same fuel, HSFO, the high sulfur fuel oil, 3.5%, and use another equipment, which is the scrubber. Which is the scrubber? The scrubber is a cleaning tower, a spray tower. You can think about a shower. We are considering water spray in counterflow with the flue gases. So this tower is installed on the stack of the ship, okay? But of course, we are talking about seawater. So seawater has a very high alkalinity, has a very high salinity. In terms of chemical engineering, all these parameters are very important for the equilibrium of absorption of the CO2 from the flue gases inside the water, okay? The seawater in this case. So marine scrubber have different pros and cons, allow low-cost fuels but while remaining compliant with regulation, the reduction of SOx emission by up to the 98%, and the cons, of course, are high cost of installation and maintenance. So we need to improve the design, the control, and the optimization. How? With artificial intelligence. Our case study is made in collaboration with the Grimaldi Group, because of course, in order to implement artificial intelligence algorithm, we need of our fuel, data, I mean. So they gave us data. We are talking about a Ro-Ro passenger ship which goes from Bilbao to St. Petersburg. And we need to be very clear. In order to build an explainable artificial intelligence framework in order to generalize the approach in all industrial application, we need to have a dataset which is made with the physics of the process. So we made an aggregated dataset from different sources. The first source is the continuous emission monitoring system of the scrubber installed of the ship. So we are talking about a PLC with a lot of sensors in terms of flue gases composition, quality of water, flow meter, temperature sensor, pressure sensor, and so on. The second source are the bunker notes. So guys, we are talking about PDF files. Why? Because in the bunker notes, we can get the amount of sulfur inside the fuel, because the continuous emission monitoring system measure just the outlet composition, not the inlet composition, because of course the regulation is made on the outlet composition. So for the company, no sense install another sensor, because it costs. The third source are satellite data from Copernicus project, because we need to know the seawater composition, because I told you the seawater composition in terms of alkalinity and salinity can make the differences into the absorption of SO2 into seawater. So we need to also other data. Of course, we have a classic data management process before to implement the algorithm, a data cleaning process based on a physically driven approach, because we removed all the data where the scrubber was switched off, all sensor faults, all the data out of sensor detection limits, all the outlier removal, starting from 50,000 samples, about 50,000 samples, until to 15,000 samples, a final data set. But of course, in order to avoid classic problems of artificial intelligence, such as overfitting, underfitting, so in order to generalize our model, we need to perform a features reduction. So we decided to use something that has a sort of high human understandability, let's say, sorry. So we decide to use a very simple person correlation. With the person correlation, by fixing a sort of cutoff, we remove 11 features. Starting from 27 features, we used at the end just 16 features. At the last part of the data management part is the data partition. We split our data set in the 80% of training set, 20% of the testing set. In order to develop our different models, we need to perform a sort of grid search cross-validation to tuning the hyperparameters of our model. In this sense, we made a 5-fold validation set starting from the training set. We decided to test 9 different AI algorithms. Why? Because we were investigating the different families, okay? Starting from ensemble models, so models made by forest of decision trees, through single decision tree models, so I'm talking about explainable model, and also model based on distances like key nearest neighbor, but also artificial neural network. And let's say you will be surprised because some model will outperform artificial neural networks in this sense. We decided to use 3 different metrics, mean square error, mean absolute error, and R square. And these are the results. As I told you, random forest, we are talking about a random forest model, so a lot of decision tree put together, outperform the performances of artificial neural networks. Here are also reported the optimal parameters. So this is the parity plot of the random forest model. As you can see, we have the target variable predicted at the experimental target variable. We are talking about the ratio between the concentration of SCO2 and the concentration of CO2, because this is the parameter which needs to be compliant with the regulation. And the prediction is very good, some outlier, but it's good. Also, the model error distribution has our normal size, so we are around 0, it's okay, but what is the explainability? Why the explainability? So, explain to discover approach. We made a physical informed dataset because we put inside the dataset a lot of physics, a lot of features related to the, let's say, the chemical engineering classical model for the design. But we need to explain, to understand, to discover, and to improve our model, okay? So we need to use, in this case, two different kind of explainable artificial intelligence interface, so post-hoc methods. The first one is LE5, which perform a sort of permutation importance because it changes, it permutes the samples of the row of our dataset for each features. And in this way, we can get a sort of table of the most important feature in our dataset. And the second one interface is the SHAP. SHAP, also Shapley additive explanation, can give us information about how this feature can impact the prediction, okay? And we can check if this way to impact the prediction is current with the classical model of design of chemical engineering. So we can check if the decision-making process of our artificial intelligence algorithm is good and it follows the physics of the problem. This is the most important things. So yes, the answers are the same in terms of weight and how to make the prediction. I can tell you, but of course, not in a deeply way, that this kind of prediction, for example, the pH of wash water after the absorption process, which decrease because starting from a neutral pH of the seawater gas to a acidic pH is current with the model. And we can see this from this sharp summary plot. The same of the total alkalinity. As you can see here, the third place of our import of our features is related to the total alkalinity that we add to our data set through the satellite data, because the alkalinity of the water is very important to regulate the pH of the water. So if you have a sort of neutral pH, it means that you can absorb more SO2 in the water. So at the end, Xi framework improves the transparency and trust in AI models for predicting marine scrubber performances. K predictors, pH of wash water, scrubber outlet temperature, because of course the temperature can affect the equilibrium of absorption, is thermodynamics. And inlet SOx concentration, yes, because if you remember, we had the inlet SOx concentration from bunker nodes, not from SEMS, are crucial for performances. Physical validation, model prediction aligned with sulfur absorption principles ensuring scientific accuracy. Operational optimization, Xi insights help to optimize scrubber efficiency and ensure regulatory compliance. Explain to discover approach reveals complex feature interaction driving better desulfurization strategies and compliance. Future works. Future works are related to the implementation of a real-time optimization based on Xi algorithms, but also to develop hybrid models, physics-informed neural network, to improve the design equation of a scrubber in terms of section of the tower, height of the tower, which means treatment time, and so on. Thank you for your attention.
Thank you so much, Piero. Guys, this is your spot now. So if you have any questions to the guys over here, please, it's the right time. Yeah, we have 2-3 questions. So let's start with the first one here in the first row. Thank you.
So I have a question for Dr. Goracci. I would like to ask you if the algorithm is able to predict all the orbits in the same way and so with the same errors, or for example, if there are orbits that are more difficult to predict, for example, if the polar LEO orbits are of the same difficulty and the errors are the same of normal LEO orbits. Thank you.
Okay, very interesting question. Actually, there are basically two cases. One case is when their orbit prediction is actually very good, talking about errors that are way lower than 1 kilometer. And there are cases in which the algorithm does not converge. And we saw that those cases are when the orbit of the observer and the target, if I don't remember wrong, are on the same plane, more or less on the same plane, or anyway, made in such a way that you don't see, because you measure the line of sight, so you measure the angle at which the object is. And if you are moving together with the target, you don't see a variation, so you just see a spot in the sky, and it stays still for the duration of the observation. So those are the most difficult to reconstruct, because the variation in the angle is practically none, so they are more difficult to reconstruct.
Which way? Okay, over there.
Hi, thank you all for your presentations. I have a question for Sara. You mentioned that your methodology went upon to classify myocarditis, right, or myocardial infarctions, right? Would the same principle be applied for tachycardias, long short QT syndromes, and other things like that?
Yes, the idea is the same. You just have, you just need the data to train the network. So whichever classifier, whichever pathologies you have, you just need the real SEG, a style transfer network that modifies it into something else, and then you feed them to the model. So as long as you have data, everything is possible.
Hey, hello. I have a question for you, Estella. First of all, congratulations for your work. It looks like a very implementable invention. And I wanted to ask, is it patentable? And if you, the ETL module with the AI interface, is it patentable? Did you patent it? And did you think about commercializing it?
Sorry, say it again. Is it what?
Is it patentable?
Oh,
Can
yeah.
you get a patent on it? Or did you get one?
The idea would be to patent the whole add-on, because the idea is to just take out the second system, to say it like that. So we have the microscope objective, the tube lens, right, which we already have, into the commercial microscopes. So the idea is to put on the microscope the L1 and L2 and the ETL, to say it like that. Yeah, so indeed it is. But there's still a lot of work to be done, because once you just place it on the microscope, you need to take into account the distances to get a well-done projection. And then you also need to take into account the voltage that you need to apply into the ETL to acquire the images. So it just, I mean, there's still a lot of work to do. So for us to be able to go to a lab and be just like, here you have your system, just put it in and it's gonna work like that. So we are not there yet, but that's the objective, yeah.
Okay, thank you. I have an additional question also for you, Gilberto. You said that the error that you measured with was less than 1 kilometer after the circumference. And I'm interested, space agencies now, when they measure how these particles travel in space, what error do they use in their measurements?
Okay, so generally for initial orbit determination, the state-of-the-art values are the ones that we used. So you want an error that is lower than 1 kilometer and that is around 10 meters per second in the velocity. This is due to the fact that this is initial orbit determination. So the goal is that you have ideally multiple observation of one object. So, and then you combine the results of the first passage, the second passage, and you want to reconstruct the orbit more accurately. Because if you try to propagate an orbit with an error of 1 kilometer and 1 meter per second, the propagated orbit with respect to the true one, after some time it degenerates. So you need more accurate precision for that. But you acquired that level of precision with multiple observations. Thank you.
Yeah, of course.
I have a couple of questions. One is for you. And I'm sorry for this, but you were, if I understand correctly, like you tried several models with your data. And you showed that the non-transparent one, which is neural networks, is not performing better than other inherently explainable model, so random forests. So why did you apply explainable AI to a model which is already inherently explainable and it gave you good results?
Because our goal is to have a sort of Xi framework to follow in different kind of application of chemical engineering. Could be marine scrubber, also some other type of reactor, but also related to process engineering, so manufacturing engineering. So it's a matter of a framework to follow. But in this case, of course, random forest is a partial, let's say, explainable, because we are always talking about a forest, randomic forest of decision tree. Maybe you can have a sort of surrogate modeling, like for example a distillation, in order to reduce the size of the forest just to a one decision tree, but not the same. You cannot have the same performances in terms of accuracy. So the explainability is always a balance between accuracy and, of course, explainability.
Okay, thank you. And I have another question for you. How did you perform the Monte Carlo simulation? Like, is there a physics formula and then you give it a seed and it gives you the... And in this case, is it the same that you use for the physics-informed neural network, like the formula for the Monte Carlo simulation?
Okay, so in the Monte Carlo simulation, we have a target generator tool that basically you can put some random parameters, which are the initial position of your observer in your target, and then you generate the arcs, so the pieces of trajectory that you want. And you do that. You can decide how to do that. You can do it with including further perturbations on the orbit, or just using Keplerian dynamics. And the same goes for the physics-informed neural network, as long as you can make the derivatives of the formulas analytically. And we use the same, we just use Keplerian dynamics, both in the propagation and in the derivation of the physics-informed neural network. This is done because all the methods that involve very short arcs use Keplerian approximations. So you don't lose precision if you consider just that one.
Then I have a follow-up questions about that.
What would change?
Because you had, like, on this Monte Carlo simulation, if I understood correctly, like a 99% accuracy.
Yes.
But isn't using the same formula for generating the data and then optimizing the neural network kind of tricking the system?
No, because the level of precision that you see is mostly due not to the physics-informed network itself, but to all the procedures that we did to make sure that that the result is robust. For example, if you just apply the neural network to all the simulation without further assistance or anything, you get a percentage of success of about 89%.
Okay.
But what we want to do, because sometimes, loss functions have local minima, okay?
Yes.
So sometimes you just fall into local minima, which are not the optimal solution. So what we did was to perform each test case like 100 times. And what we saw is that sometimes the network goes to the right solution, sometimes it doesn't. But when it doesn't, I mean, local minima have no physical meaning, so they are just, they are not orbits, okay? You get errors of 10 to the 11th, okay? So we implemented all a series of measures so that if in 100 times that we repeat the test, at least one time the orbit that you reach is correct, we implemented controls to ensure that that solution is kept and the others are discarded.
Okay.
So that results are so high because we did it a lot of tests and we found the right way to just keep the right ones. Otherwise, it would be much lower.
Because in general, as a sort of a statistician, whenever I see an accuracy higher than 95%,
that's true.
like something like
triggering
my head, and I'm wondering, right?
I know, but that's honest also because you can. We tried in different contexts to use, for example, orbits which are propagated considering J2 perturbations and third body attraction, and then try to reconstruct the trajectories using Keplerian physics-informed neural networks, and it works. So it for even more for such short arcs. So that is not a cheating, don't worry.
Thank you very much.
Thank you.
No, I was just curious.
Yeah.
didn't
No.
didn't
No,
want
because
to
our supervisor also asked us this question, so we are prepared for this.
Thank you so much.
Thank you.
We have just a couple of minutes for the last questions. Do you have anyone, guys? Oh, just a moment for the microphone.
At first, thank you all for your presentations. I have a question for Sara. It's a provocative question because for you, this methodology with AI in future can be used as primary diagnosis and not only like secondary check for medical. Yes. I ask if those methodology with AI in future can be used as primary diagnosis and not just only with second check for medical.
Okay, this is a very interesting question, and it's a topic for debate in the European Union themselves. So, in my opinion, we're not remotely close to that. First of all, because the development of sound artificial neural networks for public use, it's not there yet. There are so many variables, there's so much at stake that we're not close. Like, a lot of research is being done, a lot of papers are published, so we're not there. And second of all, I don't think it's ever gonna be the first, the most important way for diagnosing patients. And this not just for ECG, but general AI applied medicine. And this is because you need to make someone accountable for the decisions. So this is in the GDPR regulation, firstly. So someone needs to be accountable. A machine cannot be accountable. Whose fault is this? Nowadays, the fault is of the doctor that signs on the diagnosis. So if I'm signing to something and I'm taking legal responsibility for it, hell, I'm not trusting blindly of neural networks. So neural networks are going to help in decisions, but I don't see a near future where they are the primary source of decisions. So,
okay, thank you.
Okay, thank you so much for each of you. Thank you for listening to these poster presentations, guys. I really hope that you may get some ideas for your work, for your researchers. I suggest you to continue this conversation also outside during lunch or in this 15 minutes between this event and the next one. My chatbot, it's also here. So thank you so much again. Thank you for being here for the Trieste Next International Academy. As I mentioned before, we try every year to select the most interesting guys all around Europe in order to come here to Trieste Next. This is a festival which get like 50,000 people in a weekend, also with these guests from all around the world. So I hope you really enjoyed it and you enjoyed also this panel. So guys, thank you so much, and good luck for your studies and for your careers. Thank you. Thank you.